In this lecture, we will be seeing the classification of magnetic materials and also what is Bohr magneton. This is Unit 5, Lecture 5. What is origin of magnetic moment? In atoms, the permanent magnetic moments can arise due to the orbital magnetic moment of the electrons, the spin magnetic moment of the electrons, and the spin magnetic moment of the nucleus. Here we can see we are going to study about orbital magnetic moment of the electrons. We have the electron moving around in the orbit whose radius is r and area is a. Okay. And then we have the magnetic moment mu m and angular momentum L, both are anti-parallel to each other. And when the electron is moving in an orbit, it forms a closed loop and it carries a current I. So in an atom, electrons revolve around the nucleus in different circular orbits. The moving electrons give rise to electric current I, given as I is equal to minus e omega by 2 pi, where e is the charge of the electron and omega is the angular velocity. And we already seen the magnetic moment is anti-parallel to the angular momentum. Current flowing through a circular coil produces a magnetic field in a direction perpendicular to the area of the coil, and it is identical to a magnetic dipole. The magnitude of the magnetic moment produced by the dipole is mu m is equal to I into A, where we know I is the current and A is the area of the orbit. Substituting the values, we have minus e omega by 2 pi into pi r square. Multiply and divide with m. Okay. We get mu m is equal to minus e by 2m into capital L, where capital L is equal to m omega r square. What is capital M over here? Angular momentum. The negative sign indicates that the magnetic moment is anti-parallel to the angular momentum. The possible orientation of the angular momentum vector when placed in an external magnetic field is given by capital L is equal to ml into h by 2 pi, where ml is a magnetic quantum number. Therefore, mu m becomes substitute the value of L over here. So minus E by 2m into ml into h by 2 pi. So we get ultimately mu m is equal to minus E h by 4 pi m into ml. I am writing this as mu b into ml, where mu b is nothing but minus E h by 4 pi m, called as the Bohr magneton, whose value is 9.27 into 10 to the power of minus 24 ampere meter square. Bohr magneton is one unit for measuring the magnetic moment of atomic systems. For materials with completely filled shells, the orbital magnetic moment is 0, and for unfilled shell it is non-zero. So we have seen what is the Bohr magneton. So next we shall see about spin magnetic moment of electron and nucleus. Each electron spins about an axis through itself, and this gives rise to magnetic dipole moment. The major contribution to atomic magnetic moment comes from the spin of unpaired valence electrons. The magnetic moments due to electron spin align in different directions to generate a non-zero magnetic moment. When placed in a magnetic field, the atomic dipoles are aligned with their directions of magnetic moment along the direction of external field. What is nuclear spin? In addition to the contribution of electrons, the nuclear spin also contributes to magnetic moment of atoms. The contribution is negligible. In general, the total magnetic moment of an atom is the sum of the orbital and spin magnetic moment of its electrons. So next we can see the classification of magnetic materials. Now, the classification is based on atomic dipoles and the interaction between them. If the atoms of the materials do not have permanent magnetic dipoles, they are called as diamagnetic material. If the atoms of the materials have permanent magnetic dipoles, they may be paramagnetic, ferromagnetic, antiferromagnetic, or ferrimagnetic, depending on the interaction between the individual dipoles. So we shall be seeing about each. Now here we see the diagram for paramagnetism, ferromagnetism, antiferromagnetism, and ferrimagnetism. In paramagnetic materials, The interaction between the atomic magnetic dipoles is negligible. They are randomly oriented, as you see in the diagram. In ferromagnetic materials, the interaction between atomic magnetic dipoles is strong and they are aligned parallel to each other. So you can see in this diagram, all are parallel to each other. Now, if the neighboring dipoles orient in opposite directions and if the dipoles are of equal magnitude, the material is antiferromagnetic materials. Equal in magnitudes but opposite in direction, as you see in this diagram. If the neighboring dipoles are of different magnitude and orient antiparallel, the material is ferrimagnetic. So they are antiparallel, but the magnitudes are not the same. So this gives you a clear picture of paramagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic materials. Now we come back to what is diamagnetism. Diamagnetism occurs in materials whose atoms have even number of electrons, that is, electrons are paired. Due to different orientation of various orbits of an atom, the net magnetic moment is zero. When an external magnetic field is applied, the motion of electrons in their orbits changes, resulting in induced magnetic moment in a direction opposite to the direction of external field. So that is what is about diamagnetism. With the properties are they have permanent dipoles are absent. Weak repulsion is a characteristic property of diamagnetism. Relative permeability is less than 1 but positive. The magnetic susceptibility is negative and small. It is not affected by temperature. When placed inside a magnetic field, magnetic lines of forces are parallel. Examples of these are copper, zinc, bismuth, silver, gold, etc. Next, we shall see paramagnetism. Paramagnetism occurs in materials whose shells are unfilled and hence have net magnetic moment. In the absence of external magnetic field, the net moment of the atoms are arranged in a random direction and hence magnetization is zero. When external field is applied, the dipoles align in the direction of the field, giving rise to induced positive dipole moment. What are the properties? Paramagnetic materials have permanent magnetic dipoles. The magnetic susceptibility is small and positive and is inversely proportional to absolute temperature. This is known as Curie law. Spin alignment is random. When placed inside a magnetic field, it attracts the magnetic lines of force. Examples are aluminium, manganese, oxygen. What is ferromagnetism? Ferromagnetism arises when the magnetic moment of adjacent atoms are arranged in a regular order, that is, all pointing in the same direction. These substances possess a magnetic moment even in the absence of the applied magnetic field and is known as spontaneous magnetization. There is a special form of interaction called exchange coupling occurring between adjacent atoms, coupling their magnetic moment together in rigid parallelism. Properties. Ferromagnetism is due to the existence of magnetic domains which can be spontaneously magnetized. In ferromagnetic materials, large magnetization occurs in the direction of the field. Strong attraction is a characteristic property of ferromagnetism. They exhibit spontaneous magnetization. The relative permeability is very high for ferromagnetic material. The magnetic susceptibility is positive and very high. They exhibit hysteresis phenomenon, which I'll be studying about it. When placed inside a magnetic field, they attract the magnetic lines of forces very strongly. Some examples are iron, nickel, cobalt. So in this lecture, we have seen the classification of materials and we will study more about these in the coming lectures.